Thanks, everyone. My name is Max Katz. I'm a solutions architect in NVIDIA, and I serve as a general technical liaison for DOE users who want to succeed on NVIDIA GPUs. I want to do this presentation in two parts. First, I'm going to give you a general overview of what NVIDIA's software ecosystem looks like, primarily for HPC, because there's some other good content in this workshop about how to profit from a performance perspective on the deep learning framework. So I'll err towards HPC, but I'm happy to answer questions about data science or deep learning to the extent that I can answer them. And then in the second part, I want to go through a couple of examples of how I use Theta GPU for doing GPU workloads. I'll talk about what are the different programming models that are available to us on that system. And I also have a set of examples lined up that you can, like one long example with multiple steps that you can walk through if you're interested in learning how I begin to think about performance analysis, particularly when using GPUs. So that in mind, I want to start by describing the fact that all of NVIDIA's HPC libraries today are presented in the form of the NVIDIA Hpc Sdk, which is essentially a one-stop shop for HPC tooling. And so we have, of course, compilers in C, C++, and Fortran, covering a wide set of programming models, including OpenACC, OpenMP offload, CUDA, standard C++, and standard Fortran. I'll get to that in a little bit. We also have core libraries for both C++ and Fortran, as well as interfaces to the math libraries, for example, for linear algebra, random number generation, FFTs, that sort of thing. We ship with the Hpc Sdk a set of communication libraries that are optimized for working with NVIDIA GPUs. So this includes, of course, MPI, that is GPU aware, but also NVSHMEM for fine-grained direct within kernel communication, as well as Nickel for doing optimized collectives and point-to-point operations between GPUs. You might be familiar with Nickel if you're a deep learning practitioner, because that is key to making certain parts of deep learning training efficient, especially at scale. Additionally, we ship developer tools with the NVIDIA Hpc Sdk, including profilers and debugging tools. The Hpc Sdk is available for free, and we have several releases per year with new updates on functionality and performance, and it is installed on Theta GPU, and I'll give an example to its use in a little bit. The way I think about programming the NVIDIA ecosystem is that we kind of have three tiers or incremental approach to using GPU programming today. The way that you can start today, if you're using NVIDIA's compilers, is that you can actually accelerate your code for GPUs directly in the ISO standard languages. So in C++, as of C++ 17, we have parallel algorithms that allow us to directly write operations like std transform, std for each, things like that, and express an execution policy that allows us to work in parallel. And so I've shown an example here on the left where we're doing that. And that will actually, in a high quality implementation, is allowed to use an accelerator for offload. And we have implemented that in the current release of the NVIDIA Hpc Sdk. So you can do offload directly in C++ 17. Similarly, in Fortran 2008, we have do concurrent, which allows a high quality compiler implementation to use a GPU to enact parallelism on a loop, again, without any specific reference to the fact that we're using a GPU. It's just right there in the language. And additionally, in Python, we've been working on Legate, a library or package that allows us to directly write NumPy-like operations and distribute them natively across one or multiple GPUs, again, without any reference to a specific GPU. Now, in many cases, this will do just fine, but of course, there's always the possibility that you'll want to improve your performance relative to the baseline offered by the languages themselves. So we offer directive-based approaches like OpenACC and OpenMP that allow you to take specific workloads or loops in your application and then offload them with a little bit more control if you decide that that control is necessary for performance. And then finally, if you want to, you can drop down to a lower level and take direct control of the parallelism on the GPU using a language like CUDA, where you actually control directly what each thread does. And CUDA in this way is exposed in C and C++, but also Fortran and Python as well. Now, on the standardized languages front, again, I'll mention that both in C++ and in Fortran, the use of operations like stood transform and stood for each, as well as in Fortran do concurrent. These are things that can work on GPUs, and today they do with the NVIDIA Hpc Sdk. And in the NVIDIA Hpc Sdk, we have the C++ compiler is called NVC++, and the Fortran compiler is called NVFortran. If you pass the -stdpar flag to either compiler, what this says is that we want you to recognize flags, or rather, we want you to recognize operations like stood, transform, and do concurrent in the code. And if they're there, take advantage of them potentially for GPU acceleration if the compiler heuristic determines this would be a good thing to do for performance. You can also directly take control and direct the compiler which target you want to use, whether that be multiple cores on your CPU or multiple threads on your GPU, with -stdpar equals multi-core or -stdpar equals GPU accordingly. Now, one reason that you might want to do this, or that this becomes an increasingly good idea to think about, is that the complexity of hardware, of course, is not decreasing in terms of how we're delivering features. So one prime example of this is that Theta GPU has the NVIDIA A100 GPU, which is our top of the line data center HPC GPU. And on the A100 GPU, one thing that we did at NVIDIA is that we enabled the use of double precision FP64 math in tensor cores. Tensor cores are specialized hardware units that do matrix multiply type operations. And for those operations that can be cast as something like a matrix multiply, we actually have a 2x total throughput rate in terms of flops per second relative to normal fuse multiply add math. And so if you can take advantage of casting your operations in terms of matrix multiplies, you're gaining a potential factor of 2x in your throughput, which is obviously nothing to sneeze at. But of course, there's a specialized hardware units. They're not necessarily trivial to program to. They require a certain amount of specialized code in order to target those instructions. And that can be a little bit daunting for beginner or even intermediate programmers. And so one thing that we've strived to do is make these tensor cores as easy as possible for you to use at a higher level. And so there's a couple of ways that we do that. For one, our linear algebra libraries like cuBLAS will take advantage of these tensor cores, both in FP64 as well as in lower precisions for you for operations for which they make sense. For example, if you use a math library called to a gem, we'll use the tensor cores if they make sense to use. But also, for example, in Fortran, we have the ability to take advantage of these tensor cores directly. So if you write the matmul intrinsic in a Fortran code that uses the NVIDIA Fortran compiler, turns out that we can actually use a backend called cuTensor to map this to a set of operations that natively uses tensor cores behind the scenes. And so that can allow you to get high performance throughput, much higher than you would get just doing the operation directly by writing this matrix multiply yourself, but still being able to use the intrinsic in the language. And that allows you to get a significant speed up relative to even just the normal fuse multiply add approach on GPUs, but also relative to the generation before, an over 2x improvement. I'll just list here for reference, there's a wide range of Fortran intrinsics that have been ported to use this cuTensor backend behind the scenes. And so this allows you to do a pretty wide set of matrix transformations and potentially have tensor core acceleration happening for you behind the scenes, which is really nice for both performance and productivity. The Hpc Sdk ships both core C++ libraries and math libraries. On the C++ front, there's a couple of things to be aware of. Cub and thrust exist to provide primitive operations that are common in C++ approaches. For example, reductions, sorts, that sort of operation, the kind of standard algorithms that you would apply for a wide range of activities. And they allow you to have a set of reusable primitives for that you don't have to know the details of how to target GPUs for. And this is important because, as I said, the complexity of GPU architecture increases over time. And also a corollary of that is that the best way to write a given algorithm also changes over time from generation to generation. So if you learned, for example, in CUDA, how to do a reduction over an array, in 2012, the best practice for that would be very different for how you would do it in 2021 on an A100 GPU. And so using the libraries that we provide is a good choice for both productivity, but also performance over the long term. Additionally, we've been working on porting various aspects of the C++ standard library to a CUDA compatible format, and that's what we call libcu++. This is not everything in the STL, but it is a subset that we think is possible to implement and also makes sense to use on GPUs. Not everything does make sense to use on GPUs. For example, in many cases, you don't want to use std vector on a GPU for performance reasons. So that's not the thing we targeted first to do, but there are other aspects of the standard library that we're working on incorporating into C++. And then on the math libraries front, we provide a standard set of accelerated math libraries, including linear algebra for both dense and sparse cases, random number generation, FFTs, that sort of thing. So those all exist, and many of them have interfaces that are like the standard tools that you would use on CPUs. So cuFFT has an FFTW interface. The linear algebra solvers have an interface that allow you to basically hook directly as if you were calling CBLOS. These aren't necessarily the highest performance approaches, but they are a good way to start. And then from there, you can improve on performance if you want to. As I mentioned, we also ship optimized communication libraries with NVIDIA Hpc Sdk. So this comes in 3 flavors. First is HPCX, which is essentially an optimized implementation of OpenMPI that is scalable to large systems of accelerated GPU server nodes, and also has things you would expect out of such an implementation, like the ability to use CUDA or GPU device buffers in MPI calls. We have also made available NVSHMEM. NVSHMEM is an implementation of the OpenSHMEM standard for PGAS programming. This allows you to do very fine-grained, low latency communication between GPUs, particularly within a GPU kernel itself or in a stream-ordered operation. Both of these approaches allow you to gain higher potential throughput than using standard MPI approaches, because you don't have to take a round trip back to the CPU and wait there for the latency of an MPI operation to go. You can queue it off asynchronously and write an algorithm centered around that idea. And of course, there's also Nickel. Nickel's primary use case is collectives for multiple GPUs across multiple nodes for doing reduction type operations. These are very common in deep learning, but also we've seen some use cases in HPC as well. At our most recent conference, GTC, last month, we announced the availability of Leagate. Leagate is a framework that allows you to take NumPy and pandas-like operations and transparently scale them across one or multiple GPUs. So the idea is that instead of doing import NumPy as NP, you can do import Leagate.numpy as NP, and then write your standard NumPy operations. And then behind the scenes, something goes off and distributes that across one or multiple GPUs. And we've demonstrated this at very large scale. For example, we've used it successfully to scale on Summit. And the nice thing about this approach is that you can write your native NumPy code directly and still have it scale pretty well. So this is kind of the analog to using, ISO standard C++ or ISO standard Fortran. It allows you to write code that is just Python, right, and scale it to one or multiple GPUs. That doesn't necessarily mean it's the highest possible performance, but it is a pretty productive way to write your code in a way that allows you to write the same code that can be portable to multiple architectures. And what we find is that this allows pretty darn good weak scaling. So we have some examples here. This is like a CFD-like operation performing a stencil operation. And what we can see is that up to a wide range, up to 1,024 GPUs, we can get pretty good weak scaling just using native Python. Of course, we're making the problem bigger, right? And so what we're seeing here is some overhead from message passing, just like you would see if you were using a lower level approach. So it's not perfect, but it's pretty good given the fact that you're writing, Python NumPy directly. We've seen a similar thing for the pandas implementation of Leagate as well, where we can get performance up to, of order 100 GPUs that is, competitive, same order of magnitude as what you would get for a tuned implementation using MPI and CUDA. In this case, it's using a micro benchmark doing a join operation across data frames and pandas. And we see a pretty good weak scaling performance out to many GPUs across multiple nodes. And so this can be a productive way to write your Python code that takes advantage of both CPUs and GPUs. There are other approaches to using Python as well. I'm not highlighting them here in the slides, but we also work collaboratively with the developers of Numba and CuPy. CuPy allows you to write NumPy-like ND arrays on GPUs, and again allows you to write direct operations like vector multiplies and adds, and translates them into GPU offload kernels for you. And similarly, Numba has the ability to provide a slightly lower level of offloading. And so if you want to vectorize a specific function on GPUs, or you want to write even a CUDA kernel from the Python interpreter level, you can do that with Numba. And so there's a wide range of options for you for getting acceleration on GPUs. I'll pause here and see if I missed any questions in Slack. So Mark asks, if I have a program composed of multiple shared libraries, is it okay to use std_par equals multi-core for the bits that have no GPU component, and std_par equals GPU for others which do? I'm going to be honest, I haven't tried that. Based on my knowledge of how it's implemented, I don't see a reason why that wouldn't work, but I would have to check that. And that's something you could discuss with me offline if there's a use case you have for that and it doesn't work. We can look into whether it's possible. But I apologize because I've never actually tried that, so I can't be certain that it does work. And then another channel I see, does the Eigen library take advantage of NVIDIA SDK libraries? To my knowledge, no, today Eigen does not do that. There are implementations that of kind of standard micro math operations that you might want to look at. In particular, if you're familiar with Cocos, Cocos kernels provides you a set of vendor agnostic implementations of kind of core operations in various math approaches that you might want to look at if that's of interest to you. And then, which tool in the NVIDIA SDK facilitates communication among multiple GPUs on a node? So I'll return to this slide here. So there's a couple different ways to do that, and it depends on what approach you're using. So if you're an HPC programmer used to writing your message passing directly, you might use CUDA aware MPI. What that allows you to do is use your normal MPI operations and pass to them directly pointers that may live on a GPU, and a high quality CUDA aware MPI implementation, such as the one we ship with HPCX in the NVIDIA Hpc Sdk, can use that and send messages directly between multiple GPUs within a node, or potentially even across nodes. If you're like a deep learning person, then you might be using Nickel under the hood to do, for example, the all reduce operation for gradients across like an ensemble of deep learning training processes. And typically you're not writing Nickel operations directly. That's implemented for you either by the framework. For example, you might be using TensorFlow's mirror strategy or PyTorch to read a data parallel. Or if you use something like Horovod, which is built on top of MPI, that can also use Nickel under the hood. Returning back to the HPC point, NVSHMEM also allows you to write communications directly between GPUs, but with the benefit that you can do it as fine-grained a level as the individual GPU thread sending one message from a GPU to another GPU. For different Leagate operations for multiple GPUs, does it work on multi-node GPUs, or do all GPUs have to be connected to the same host node? Leagate is designed to scale across multiple nodes. And so we have demonstrated Leagate at, I don't know if it was like the full system scale of Summit, but we did a pretty large chunk of runs on the Summit supercomputer across both GPUs within a node as well as GPUs across multiple nodes. And that's really the core design point of Leagate, is to allow scaling to multiple nodes. Okay, that looks like all of the questions for now, so I will continue. Switching gears a little bit from the programming models, I want to talk about the developer tools. So the main performance analysis tools come in the Nsight product family. These are 3 tools that are available to you. Typically where you start is with Nsight Systems. What Nsight Systems allows you to do is have application-wide performance analysis that performs analysis at the full system scale, so the CPUs and the GPUs. And this allows you to collect a timeline of your application, showing you where the GPU activities were, as well as where the CPU activities were, so that you can get a sense of what parts of your workload are actually happening on GPUs. Once you have that timeline, you can then ask questions like, am I spending most of my time on the GPU? This is a thing that you generally want to be the case, because the GPU for most math operations has much higher potential throughput than the CPU. And so you don't want to be spending 90% of your time on CPUs if you're using a GPU accelerated node. So Nsight Systems can help you do that. And then once you've used Nsight Systems to profile the workload, you do some refactoring, you're now at the point where all of the majority of your workload is represented as actual GPU kernels, which are just the compute constructs on GPUs. Then you would dive into Nsight Compute. Nsight Compute allows you to optimize specific CUDA kernels. Now, CUDA, you may be familiar with the term CUDA as the low-level approach for targeting NVIDIA GPUs, like CUDA C++. But CUDA is really a broader term than that. It really refers to the core or base level of the NVIDIA accelerated computing ecosystem, above which everything is built on top of. And so regardless of whether you're using CUDA C++ or Numba or CUDA Fortran or OpenACC or OpenMP or these ISO standard languages, at the end of the day, they're all generating the same kind of machine code, which we can call CUDA code if we want to. And the benefit there is that we can use the same tools to analyze all of those things. And Nsight Compute then you can analyze performance of compute kernels from a wide variety of different higher level languages. Additionally, we have for debugging Compute Sanitizer, which is kind of like Valgrind for GPUs, allows you to detect memory races and uninitialized memory accesses, that sort of thing, as well as a CUDA-aware extension of GDB, CUDA GDB, which allows you to set breakpoints, inspect the state of threads, that sort of thing, just like you would do for debugging things on GPUs. This is an example of the kind of thing that you would get with Nsight Systems. It shows you a timeline of your application where increasing from left to right is time. And then the idea is that you have different rows in the application that show you or trace different kinds of activities. So you have rows that trace CPU activities, and so you can see where the load on the CPU is, as well as any calls, for example, into the CUDA runtime, which is what ultimately launches memory copies to and from the GPU, as well as launches of these kernels, these compute constructs. And then you can see rows that show you the actual workloads on the GPU themselves. And then you can use that to correlate where the GPU workloads are relative to the CPU workloads, and then help use that to build a model of the performance of your application. And I can show you an example of this a little bit later when I get to the demo portion. In addition, you can dive into any one of these rows and really see a great amount of detail. So for example, you can highlight a particular kernel launch. These again are the specific compute workloads, and then get some statistics about the performance of that workload. So this is an example where we selected a particular kernel, and then we hover over it, we get a tooltip that shows us when and where it started, how many threads it used on the GPU, some other information about what its memory demands were. And this can be very useful because just with this level of information, we can answer some first order questions about whether this workload was even appropriate for use on GPUs. The way I typically think about this is that GPUs can field something like of order 100,000 threads at any one time, at least NVIDIA GPUs. It can be in flight at any one time. And so you need to have something like at least 100,000 degrees of freedom in your problem to use the GPU effectively. And so you can figure out from this information how many threads are being used in this kernel. And if the answer is like 100, then you already know that there's no way that that kernel can saturate the GPU's performance, because you're just not using all of the GPU's compute resources that are available to you. One nice thing that I'll mention in the hands-on exercise that's I prepared is that you can use NVTX, the NVIDIA Tools extension for profiling. These provide APIs that you can write in your program for manual instrumentation. And these allow you to essentially, using human readable strings, mark up or instrument your application. And then you're basically writing those names directly into the profile. And so you can correlate parts of the code that you understand with a name that you understand in the actual profiler itself. And these are shown in the Nsight Systems timeline, which I'll give an example of later. NVTX, this tools API, is exposed in several different ways. It's exposed in C and C++ and Fortran, but also in Python, both directly in Python for like NumPy approaches, but also in the deep learning frameworks. There are ways to use this as well. The way that you collect the profile with NSI systems is pretty straightforward. NSys is the command line tool. So you do NSys profile and then the name of your application. It generates a report file. That report file can either be inspected at the command line or it can be inspected in the user interface. And it's usable both directly, like a bare metal usage, but also you can use it within containers. And so, for example, if you're using the deep learning containers on Theta GPU, you can collect the profiles within a Singularity container and get information that way as well. Now, I mentioned that NSI Compute is kind of our companion tool. NSI Compute allows you to profile the performance of a particular kernel. And this basically allows you to understand for that compute workload, which is kind of the indivisible unit of work on a GPU, what percentage of peak throughput was I getting? And this can be broken down into both compute throughput as well as memory throughput. And this helps you answer basic questions like, am I compute bound? Am I memory bandwidth bound? If not, why not? And you get a pretty detailed set of analysis sections that dive into different parts of your workload and help you understand why I did or did not achieve peak throughput. NSI Compute can be used at both the user interface and command line, just like NSI systems can. And it's also highly customizable. So we provide a pretty decent and thorough set of analysis framework sections for you to use right off the bat. But if you want to customize it, there's a pretty wide range of customizability available to you for answering very specific targeted questions that you have. NSI Compute also allows you to inspect the source code of your kernels and correlate them to a sampling tool that we can use when we profile the application. So we can run through your workload, collect samples of where we are in the kernel, and then correlate that back to your source code. And that allows you to build some model of, in some sense, what the expensive parts of your compute kernel are. And so that's going to be a useful tool. You know, I would typically recommend that for relatively advanced developers. That's not something you should dive into first thing, but it is available to you for high-level optimization, or low-level optimization, I should say. And then the command line tool, NSI Compute, is available as NCU, and then the name of your application. NSI Compute has a fairly high level of overhead due to all of the metrics that it has to collect for analyzing your kernel. So I do recommend using its options to restrict the level of profiling that you do. For example, profiling particular kernels or profiling only a certain number of invocations of them. And I have a couple of examples of that in the README for the in the repo that we have available for all you all today. So there's some practice that you can get with that if you want to. Okay, that is the first part of the talk I wanted to complete. Again, I'll check for questions. Is NV Fortran available on Summit 2? The answer is yes, it is available on Summit. Are there league examples we can try on Theta GPU today? I didn't have time, unfortunately, prepare League on Theta GPU. It requires a little bit more setup right now. For both Numba and CuPy, which I do have examples of, those are a very simple, straightforward conda install, and I have the instructions for that in the README. For League, it currently requires a little bit more setup, so I didn't choose to include that in the README, but I'm happy, like after today, to add some instructions for the setup. If you're willing to do a little bit more work to get that setup done, I'm happy to follow up on that. Okay, can NSI Compute help in optimizing Cocos code when using the CUDA backend? And if so, do I have any pointers to tutorial material? The answer is yes. Cocos ultimately generates CUDA code, like you said, behind the scenes. That's one of the things it can do. And Cocos is just C++, right? There's nothing magical about it. It's just C++ code. And so like any other C++ code, it can be analyzed using NSI Compute, and you can correlate your C++ performance, your C++ source code in the source code viewer if you want to. And just like any other compute kernel that uses CUDA under the hood, it can be profiled with NSI Compute. Now, because Cocos exists at a higher level, that means that you may want to not necessarily see things at the level of the low-level CUDA constructs, but may want to think about what kinds of Cocos-like transformations would I do. I would point you to the Cocos tutorials, and I can provide a link to that after I'm done, that Kristen Trott and others did last year. They provide a pretty thorough set of overviews, and there should be some good information there on performance analysis that I can link you to. Okay, so Alfred asks, when I'm on Theta GPU, git pull seems stuck. Do I need to load some module? That reminds me of the point that I only uploaded my exercises like an hour ago. So if you already pulled the repository, you will need to do a git pull to refresh. And by default, that does not work on a compute node just because of some HTTP settings. So I'm pretty sure the ALCF folks will be able to help you out with that. But a quick solution would just be to log out of the compute node. Then you can do a git pull from the login node, and then you can go back to the compute node. That would be an easy way to do it. Okay, that looks like all the questions I saw for the moment. Okay, so with that in mind, I wanted to talk about a couple of the simple examples that I provided for using NVIDIA GPUs. These are targeted to Theta GPU in particular. So if you are set up on there and you know how to get a GPU already, then this should be pretty straightforward. If you don't, please ask in the Slack channel and we'll be happy to help you with that. Now, I happen to have a Theta GPU node already up, and I have, you can see that there's 8 of these A100 node, GPUs available in this particular node that I'm on. And if you look in the perf workshop repo that I was talking about, this is there's an 04 NVIDIA directory, and that's where the examples that I provided are available. And I have a README that's available here if you want to take a look. And what the README does is it has 2 sections. One is that it has a few example codes that show you how to do DAXP, double precision, A times X plus Y, in Fortran, C++, and Python. So you can get a sense of the different programming models that are available to you on a system like Theta GPU. And these are just all here, the various codes. All of the DAXP codes are here for you to inspect if you want to. And the README has instructions for how to play around with them. So as an example, if I want to play with the do concurrent in Fortran, I can just go ahead and open up DAXP stdpar.f90 and take a look at what this code does. You can see that these are very, very simple toy codes. Again, I'm just performing the DAXP operation A times X plus Y, and then storing it back in the vector Y. I'm just providing some, kind of silly initialization for these vectors. And the key thing here that I want you to pay attention to in this source code is that there's absolutely no reference to GPUs, right? There's no reference to CUDA in this code. There's no reference to GPUs at all. This is standard Fortran that you would write and could target normal CPUs. But with the NVIDIA Hpc Sdk, in particular the NV Fortran compiler, you can target this to run on NVIDIA GPUs. And so I provided the compilation line that you would need to use for that in the README. And so if you look at the standard language parallelism, you see that there's the Fortran thing. So the way it looks is that you use NV Fortran as the compiler, and then -stdpar means that we want to recognize these standard language parallelism constructs like do concurrent or std transform and offload them to the GPU. And then that's all you need to do. So if I copy and paste this line into the command line, then I can go ahead and run that. And to do that, I need to have the NVHPC module loaded. So that's available to you like so, that just module load NVHPC, and I mentioned that in the README, and then I can compile the code. Oh, I need to have the correct module loaded. Yes, I want to load NVHPC 21.3, sorry. There we go, that should work. And at the end of this, I will have this binary DAXP stdpar, which I can just run. But the application didn't have any output. So I recommend just running it through the Nsight Systems profiler to verify that this actually ran on the GPU. I mentioned that this is kind of the default invocation of Nsight Systems. So nsys profile means collective profile of my application. And then -- stats equals true means print a summary of the output to standard out at the end. So I can do DAXP stdpar. And what it will do is we'll print out a summary of all the activities that were related to the GPU. And we should see, if everything worked, an indication that, so this prints out in several sections. The CUDA API are all of the APIs that were called on the CPU to prep the GPU. So we called some things to allocate some memory to launch a kernel. And then CUDA kernels are the actual compute workloads that launch on the GPU. And so this allows us to verify that indeed a CUDA kernel was implemented and did run on the GPU, and then ran for some amount of time, and then computed this DAXP operation over 1 million elements. And so with a simple compiler flag, we were able to tell this code to run on the GPU. But notice that because it's just standard Fortran, I could have just dropped off the std_par flag, and then this just becomes a normal kind of CPU code. No acceleration is available, and so I could profile that, and I would expect to see no CUDA kernels that are launched to perform the do concurrent operation. And indeed, that's what we see. Now, the one thing that I'll note is that when you use this -std_par operation, it handles both memory as well as compute constructs for you. So you may know, if you're familiar with GPUs, that by default, GPUs have a separate RAM than CPUs do. And so on many platforms, particularly standard x86 platforms, we need to have some sort of memory transfer between the CPU and the GPU to have high performance offload on the GPU. And so the NVIDIA Hpc Sdk compilers take care of that for you if you're using the standard parallelism. They allocate all dynamic memory allocations for you using managed memory under the hood, which can migrate on demand between the CPU and the GPU, and that allows you to use the GPU transparently. Okay. So that's how you do it in the Fortran example. There's also a C++ example if you're more inclined to use that. So this is the example in Fortran. We're choosing to use a std transform here. And again, this is just a normal C++ code. I'm just allocating some pointers in using normal malloc, initializing them. And then to perform the DAXP operation, what I'm doing is I'm using std transform, which takes an execution policy. In this case, I'm choosing to use the execution policy, which can run in parallel and which assumes no ordering or dependency between the individual operations. And then if you're familiar with std transform, you know it takes an iterator, which has like a first value and a last value, and then the corresponding first value of the second array, and then the location of the output. And so what this does, and then you provide it finally a binary operator, which takes the pair of input values from X and Y, and then does something with them. In this case, I'm just writing a simple lambda function, which performs A times X plus Y, and then we return that and then store it in the corresponding location in Y. So that's how you use std transform. And again, this is standard C++ and C++ 17. This is not NVIDIA specific code, and you can use that to offload on the GPU. And again, you would just use NVIDIA C++ and then the -std_par flag to compile and run that. And you're welcome to try that if you want to. I mentioned that we also have directive-based approaches. So for example, we have OpenACC and OpenMP. So if I take a look at the OpenMP offload example, and I'll look at it in Fortran, this is DAXP OMP.f90. And we see that again, I do the same thing where I'm just allocating some arrays as normal in Fortran, just X and Y, double precision allocatable, initializing them the same way. But I'm using OMP target to indicate that I want this to be offloaded. And I'm using OMP target teams loop. In OpenMP5, target teams loop is, we consider it recommended for performance reasons, because this gives the compiler a wide degree of freedom to optimize this for NVIDIA GPUs. But if you're more familiar with OpenMP4, you can use target teams distribute parallel as well. And then this should compile and run. I won't say too much more about OpenMP. There's already content in this workshop about that, but I did want to emphasize that this is available to you as an option for incremental offload in Fortran and C++. And there's a similar thing like this in the C++ example as well. Additionally, there's the Python examples. And so I have two examples. I have NumPy and CuPy. So the CuPy example is the one that is the closest to normal NumPy operations. And what happens with CuPy is that CuPy allows you to write NumPy ND array-like operations, but that can run natively on a GPU. And so in this example, I'm creating some normal NumPy ND arrays that are float 64, X and Y. Again, and I'm initializing them the same way as I did in the Fortran and C++ codes. And I'm creating CuPy arrays from these NumPy arrays. And CuPy arrays by default live on a device if it's available to me. And so I can just basically create a copy of this X array And then now I'm using d_x to indicate this is a device array, happens to live on the GPU. And then I can natively perform operations that work on these NumPy and arrays in CuPy directly. And so you can see I'm just setting dy equals a times dx plus dy, and then this can generate kernels under the hood to operate in a high performance approach on the GPU. And notice that other than declaring the arrays differently, we really haven't done much differently. This is standard NumPy-like operations. And you can even elide the copies if you want, right? I don't have to, I could have initialized this on the GPU. I would just then have to have some sort of GPU workload which actually initializes the data. Now, if you want to express a custom operation like this, which performs some particular operation across a wide range of indices, one way to do that is using Numba. So Numba allows you to write vectorized functions or even low-level CUDA kernels if you want to, that can be broadcast across a set of values using normal NumPy universal function approaches. So here's an example of a universal function DAXP, which takes as inputs a, x, and y and returns a times x plus y. And Numba provides the @vectorized decorator, which allows you to specify a function signature and a target, in this case CUDA, saying that we want to run this on an NVIDIA GPU. And in this case, we're allocating some NumPy arrays, we're initializing them, and then we're performing the DAXP operation. And because we decorated this with @vectorized and a target of CUDA, this can actually run on the GPU natively. And will handle all of the work for us of copying the inputs to the GPU, computing the result, and then copying them back to the CPU.
Sorry, Max. In the previous example, how do you get the result back? Because those were created on the device. The dy is living on the device, right?
Right. So in this case, dy would be living on the device. CuPy provides an intrinsic that allows you to basically copy the result back to a NumPy array if you want to. The documentation is pretty clear on this, and I can point that to you if you need to.
Thanks.
Yep. Okay, I'll just pause here for one more second if there are any other questions.
So NVIDIA is offering those programming models.
Yes.
Do they interop with each other?
Yes. In the NVIDIA Hpc Sdk, the design point is that you can essentially use all of these interoperatively. And so one way that you can approach the process of working on GPUs on the NVIDIA platform is, if you can, or if it's possible, or if you're interested, you can start with the ISO standard approaches. For example, write everything with do concurrent or std_par on C++, like std for each or std transform. And then if you find that either the standard language doesn't support the operation you want to do, or the implementation that we have isn't high performance enough for what you targeted, then you can incrementally take parts of your code and then write it with OpenACC or write it with CUDA. And those can all interoperate with each other. And so you can certainly have an application that has some do concurrent if you're in Fortran, some OpenACC directives, some OpenMP directives if you really want to mix those two, and even CUDA Fortran as well. These things can all work together. This allows you to incrementally port your application. And if you have particular kernels that are really performance sensitive, for which you want highest performance that only the lower level approaches can offer, then you can use those together.
Okay, I understand this point. Thanks. So I was trying a CUDA Fortran code and try to put OpenMP, and I failed. So I assume it's a bug rather than, okay, we don't support it.
Yeah, it's either a bug or you didn't use the right compiler invocation. You know, I can help you sort that out offline.
Yeah, thanks.
Let me see if there were any other questions I missed.
Can I ask, does CuPy have the standard functions of NumPy, like the statistical functions?
CuPy has a subset of those operations, yes. So, you know, it was designed for solving a lot of these standard, like data analysis, data science type workloads. And so it does have a pretty standard set of things like performing like statistical reductions, that sort of thing, the kinds of standard operations you would expect. It's not literally everything, because at the end of the day, somebody had to go and write a backend on the GPU for each operation, but there's a pretty wide set of things that are available. Okay, in the last part of this presentation, what I wanted to do is mention that there is also a kind of walkthrough performance analysis exercise in this same directory. And so if you look at the README, then you'll see that there is this performance analysis walkthrough section. It might be prettier to look at in the GitHub repository if you want to. But basically the way it works is that we have this simple toy code which performs Jacobi relaxation. And Jacobi relaxation is not interesting in the sense that you've probably seen this example used to death in performance analysis cases. So the goal here for why I chose this example is not because it's interesting from a performance analysis perspective, but because you probably already do know it. And so this allows you to focus on what I consider as I think that there's a certain mindset that you should have when it comes to performance analysis on GPUs. I find that the people who are most successful using GPUs have a methodical approach to how they target the process. And so many people, I see this all the time. I go to a lot of hackathons and work with developers, and all the time I see people who have learned things in the ether about how they believe GPUs work. For example, that the first time that they write a kernel, that the immediate thing that they need to focus on is the memory access pattern, or that they have divergence between threads, so like different threads are doing different things, and they've heard that doesn't work well on GPUs. And they might be right about that in a sort of abstract sense, but I don't recommend that the way that you approach GPUs is to think about it in terms of a set of lessons that you learned that you then inspect your code to look for and then fix. Because while you should, to be successful on GPUs, have an intuitive mental model of the architecture and how the performance model works on the GPUs, you really need to assist this liberally with developer tools to help you understand, at this time, what does my application look like? Because you might be confusing yourself into looking at just the entirely wrong part of your application. And so a methodical approach where you use the developer tools at every point in your refactoring process to understand where am I now and where should I be going next is really important, I think, for using GPUs effectively. And I think this is true on any vendor's GPUs, right? Just the way that you use GPUs is different from the way that you use CPUs. And so you really need to have a methodical approach that does not start from your assumptions about what makes sense in GPUs, but rather you confront your assumptions, your mental model, with what the developer tool is telling you about what's happening. So with that in mind, this example is pretty straightforward, right? All main does is it initializes some a scalar field. In this case, like my mental model was the equilibrium temperature distribution on a metal plate that has boundary values of temperature fixed. And then it does a simple iterative loop where we perform a Jacobi relaxation step. We then swap the old data and the new data. We check what our current error was, our L2 norm of our error, by just checking the difference between the old and the new. And then we stop when we've converged to some answer, right, within some tolerance. And so there's nothing special about this code. You've probably seen this example before. And these are the individual functions that are used for doing this. This is the actual relaxation step that basically just averages out at any given point in a two-dimensional grid, the neighbors in that two-dimensional space. And then this is the operation that just copies the old data and the new data. So again, nothing particularly interesting here. I use it to focus on the set of steps for performance analysis. And so what I've done in the README is I've provided basically a set of optimizations that I've made that you can follow through. And they give you a sense of how I think about performance analysis. And so where I start is thinking about the fact that the very first thing you need to do in any application is understand what is the bottleneck to begin with, right? On the CPU code, where is the time being spent? Because that'll give you a sense of what to focus on and what not to focus on. While it's not always true that what is the bottleneck on the CPU is also the same bottleneck on the GPU, it is important to identify which are the computationally expensive parts of your algorithm, because those are the ones you're going to want to use on the GPU, right? And if you find that the bottlenecks in your CPU code are not compute heavy parts of your code, then that's a pretty good sign already that you're going to run into trouble on GPUs, because GPUs aren't designed for serialized workloads that don't parallelize well. So with that in mind, the first thing that I do in any code before I even write any GPU code is I use this NVTX, NVIDIA Tools Extension API, that allows me to mark up sections of my code with an instrumentation that I do, which allows me to annotate where I believe the parts of the code that are likely to be important are. And so if I look at each optimization step, this one isn't an optimization yet, has a name. So the first one is Jacobi step 1.cpp. And basically what I do is I add this instrumentation API, NVTX. And the way it works is that I push and pop ranges onto a stack, and I just give it a name. So like the part where I allocate the initial memory for my scalar fields is called allocate memory. Then the part where I fill in the initial data is initialize data. And then here's the part where I do a individual Jacobi relaxation step. And then here's the part where I do the swap between the old and the new data. And I believe that's all of the ones that I have. And oh yeah, the one here at the end that clears up the memory. So I've just added a few instrumentation APIs to my code. And the nice thing is that the Nsight Systems profiler can show you, knows how to interpret these and can show you some information about these. And so I provided the steps here for compiling and running. So I'm going to use, in this case, I chose to accelerate it with CUDA C++. So I'm going to use NVCC, the CUDA C++ compiler, to compile it. And then I provided here the compile flag that you can use to generate this. And so you can see the other thing I've had to do here is add the -nv tools x. This is the library we need to use that API. And then I've also provided the Nsight Systems profiler invocation that you would use. And because I'm using this --stats equals true flag, what it does is it prints out some summary at the end about what's going on. And so the code prints out every 25 iterations what the error is, right? The difference between the last step and the new step. And I've told it to converge after we reach an error of 0.0001. And so you can see it takes almost 600 iterations for this thing to converge. And it does it in about 0.02 seconds on the CPU. And then the Nsight Systems output has this section where it collects statistics on all of the NVTX ranges. And so you can see here, this name, Jacobi step, that's the name I gave it in the code, right? So the profiler knows about this and can interpret it. And it shows me that 70% of the time is spent in this Jacobi step section of the code, and then 30% of the time is spent in swap data. Since these are the computationally expensive parts of the code, that's what I expected, right? It would be a surprise to me if like the allocated memory bit were as expensive, anywhere near as expensive as the actual compute part of the code. And then what you can do additionally, now that you've generated these profiles, is you can actually copy these to your local system and then inspect them in the Nsight Systems user interface if you choose to. So I'll just briefly do that. And the way that you could do that, I generally recommend using the process where you copy the report to your local system and then analyze it in your local installation of the user interface. It is free to download. And the reason is just it'll be more pleasant, I think, than like trying to do it over an exporting type approach. And so you could just SCP the file down to your local system. So for example, I just copy the path to this file. The file extension is .qdrep. So that's how you know that that's the one you want to get. You just copy that to your local system. And then what I could do is I could open up Nsight Systems, and then I would just find that file on my file system, Jacobi step 1, and I would open it up. If there's any errors here, you can ignore them. Those are not super relevant. And then basically what it shows you is a row for each of the relevant parts of the instrumentation you've done. In this case, the profile is pretty boring because we have no GPU activities yet, but I do have a row for NVTX. That's the instrumentation I added. And then if I zoom in all the way, I can see that basically it's just one Jacobi step and then swap data step after another, right? And it keeps on going until we converge. So if this is my baseline, then when I start wanting to see GPU activity there, then I would expect to see some difference in how long these take. And then that's the goal, is to iteratively go through this process and then do it. So for example, if I jump to, I don't know, step 5, which is somewhere down the optimization process, I encourage you to actually go through these step by step, so you can see like what happened in steps 2 through 5. But if I just were to skip to it and then generate a profile for it, then this is already at a point in the walkthrough where we've done some work on the GPU and it works reasonably effectively. And if I copy that report file down to my system and then load it up in the viewer, then I can see the GPU activities happening. And now you see that there's a CUDA row, and these are the GPU activities. And then you can dive in and really, if you want to zoom into a very detailed part of the workflow, and then you see, for example, a part of the workflow where here's that Jacobi step operation, and then here's that swap data operation. So you can see here are all of the compute kernels that are running, and then correlate them to the section of code that I was interested in. And so this allows us to correlate parts of the code in the CPU with the corresponding operations in the GPU. And then you would compare these two things. And then as you make iterative adjustments, you see, do these kernels or these NVTX sections get faster or slower? So for the sake of time, I'm not going to go through that step by step, but I do encourage you, if you're interested, to go through that README and look through each of these steps and think about what I did in each step. And I'm happy offline on Slack to answer any questions about that performance exercise. And of course, you can work on that throughout the day. So with that, I will stop and answer any other questions. I see I have a Cocos implementation and an equivalent CUDA implementation. Is it possible to get some consultation on the Cocos CUDA implementation? I'm happy to take a look for you at that if you want to. One nice thing about Insight Compute is that allows you to compare the two directly. So you can compare the two implementations. So I'm happy to, when I have a little bit of time later today, to work with anyone who wants to ask me detailed questions. Any other questions about the NVIDIA platform?
Thanks, Max. I encourage attendees, if you have questions, you can just unmute yourself and ask the questions or put it in the Slack message.
Hi, so since we have time, what was the conclusion of your GPU run for this Jacobi example? Does it show that GPU is helping or no?
So that's a good question, and the README goes into it in some detail. But the actual upshot of the step of the walkthrough is that in the initial implementation of the code, the GPU does not help. And if I look at the initial code, what happens here, if I just look at the initial code, I'm solving this problem on a 64 by 64 grid. And it turns out that that's just not enough work to saturate the GPU. And so two things will happen. The first is that it actually takes of order half of a second just to initialize an NVIDIA GPU. And so if the compute part of your workload takes less than a half a second, then you're already bottlenecked by just initializing the GPU. And we saw that when we ran the CPU part of this workload, that it ran in like 0.01 seconds. And so even if I could bring that down to exactly 0, infinitely fast with the GPU, just initializing the problem would be like orders of magnitude larger than that. And so this problem is not big enough to use a GPU. And so what I walk through in this example is that you have to make the problem bigger in order to profitably use a GPU. You have to make it super big. And so what I found is that only when n was like 2048 for this example, did it really make sense to use a GPU, right? We had to have a very large grid for the GPU to like be a clear win over the CPU. Otherwise, these other things become a bottleneck, like initializing the GPU, allocating memory, copying into the GPU. These become a bottleneck if the grid is too small and if you don't expose enough work to the GPU. So yes, in this example, the GPU can be a big win compared to the CPU. However, it needs to be a big enough problem to amortize the overheads of just using the GPU to begin with.
Thank you. That makes sense.
Okay. On Slack, is NV Fortran available somewhere else or just on Data GPU? It is available in other locations. It is not provided directly with CUDA, but it is provided with the NVIDIA Hpc Sdk, which is a free download if you just Google it, and I can link to it in Slack. That includes both the NVIDIA Hpc compilers as well as a subset of the CUDA toolkit for kind of a complete implementation of HPC relevant GPU offload for NVIDIA.
You mentioned that legate may not be necessarily the best way to go for performance. What do you expect for performance penalty compared to CUDA?
You know, it's hard to say. I gave a couple examples in the slides where it was actually pretty good compared to a tuned MPI and CUDA implementation, but we were also choosing examples that were not that hard to get right. Like we were choosing that stencil operation that I was showing you. Like it's hard to really do that super well on a GPU because you're fundamentally memory bandwidth bound. And so like you can get rid of the bottlenecks, but you can't be perfect on that. And so in that example, we were achieving like 90% of like a tuned CUDA performance. There are certainly, you know, arbitrarily complicated algorithms where the Python implementation using just NumPy does not get you all the way. But for things like multiplying two matrices together or adding the vectors together, those kinds of standard Python-like operations, you're gonna, in both NumPy and CuPy, but also Leagate, you're gonna get a pretty good fraction of peak performance. Like I can't give a universal number, right? But like, I wouldn't be surprised if you consistently got 80% or more of the CUDA performance using this approach. And then if you found that it really was just tanking on something, then you could then dive into a lower level approach like NumPy for those specific operations. But we're really focusing on making you not have to do that as much as possible with Leagate. Okay, I have run out my time, and so I want to talk to people and give people time for